Hello everyone, welcome you to the course UAV Design. Today we will be seeing the topic UAV design process. In the last lecture we have seen the UAV conceptual design. In this lecture we'll continue from the conceptual design and we'll finalize the design process, preliminary design phase. This phase transitions the UAV from basic configuration to preliminary sizing and subsystem definitions. It focuses on refining parameters to a practical and verifiable level. During the preliminary design phase, the following four fundamental unmanned air vehicle parameters are determined. Maximum takeoff weight, which is UAV maximum takeoff weight, wing reference area, engine thrust or engine power, preliminary autopilot calculations. These parameters dictate the UAV's overall size, performance, potential, manufacturing cost, and complexity in downstream design. If a jet engine was selected during conceptual design, thrust is calculated. If a propeller-driven engine was selected during conceptual design, then power is calculated. There's a difference in thrust and power. The entire calculation changes. Other secondary parameters estimated, which includes zero lift drag coefficient, that is CD0, maximum lift coefficient, that is CL max. These play a role in preliminary aerodynamic and performance estimations. The preliminary design phase will have UAV performance design requirements from our conceptual sketch. It will include maximum speed, range, endurance, rate of climb, takeoff runway, stall speed, payload. Based upon these requirements, we'll have our UAV conceptual design ready. Once the conceptual design is ready, we'll determine the unmanned air vehicle's maximum takeoff weight. With these requirements, we will determine the maximum takeoff weight. So, in general, the maximum takeoff weight will include payload, crew load, crew weight, empty weight, and fuel weight. The takeoff weight is divided into these segments: payload, crew load, empty weight, and fuel weight. For unmanned air vehicle, there is no crew load, so it will be payload, structure of the aircraft, that is empty weight, plus if it is jet engine, which will have fuel, then we'll have fuel engines, we'll have fuel weight, else it will be only payload and empty weight. This empty weight will include the batteries, the power systems which will drive the aircraft. Once the maximum takeoff weight is determined, then the wing area is determined and engine thrust or power is determined. After this, when we enter the third phase, it will derive the autopilot primary characteristics. Once we have these three done, we'll have the output of maximum takeoff weight, wings surface area, that is planform area, thrust or power, and autopilot configuration. The design process during this phase proceeds in the following sequence. First one, estimation of UAV maximum takeoff weight from the flowchart. Based on the statistical techniques using, first we'll define the payload, how much weight the aircraft is supposed to carry. This payload may include the weights of equipments or devices which will be accommodated in the fuselage for the mission. It will also include sensors and it will also include cabin pressurization system, which will ensure the sensors and the devices which are being constantly used will not heat. It will ensure that heat is being maintained to the normal temperatures. So for that we need cabin pressurization systems. And based upon the mission range, how many kilometers or how many miles or how many nautical miles that unmanned air vehicle has to travel, based upon that again we'll have this maximum takeoff weight. Maximum takeoff weight is generally, this is a simple mission profile. 0 to 1 is our ground roll and takeoff. 1 to 2 is our climb. 2 to 3 is our cruise. If there is any loiter, we'll have here 3 to 4. Then again we have touchdown, then ground roll and land. So during this phase, right, based upon the mission range, we estimate maximum takeoff weight based upon the mission range, where we'll get the range value. Based upon the range, right, that is between 2 to 3, which is our cruise, right. Based upon the range requirement, we'll calculate our maximum takeoff weight, and also we'll have endurance. These are the two terms which we generally use in estimating maximum takeoff weight. These steps provide a first level weight estimate. This will give you rough value, and till the guess value is not equal to the calculate value, we'll continue this process. Once this guess value is equal to the calculate value, then we'll stop the iteration. This is an iterative process. This method involves approximation and may include inaccuracies. So for that reason, we go for iterations. Step 2, determination of a wing area and thrust or power. Based on performance requirements, we estimate the stall speed, Vstall, which is nothing but the cruise speed. Maximum speed, it can be more than this cruise speed. Then takeoff run, how much runway we need. Range, what's the distance my aircraft has to travel in one payload of fuel. Then rate of climb. Next, all these data which are being estimated, which it will be compared with a matching plot or a matching chart which is developed by NASA. It was introduced by NASA and enhanced further by referenced author. This technique is graphical and allows simultaneous matching of thrust, power and wing loading. It is considered more accurate and reliable than maximum takeoff weight statistical estimations. This matching plot and matching chart, actually this gives you the values between for wing loading and for thrust or power with respect to MTOW. The third phase is preliminary autopilot calculations. It involves the basic control analysis based on mission needs. It forms the starting point for later flight control design and simulation. Design of UAV subsystems. Subsystems design turns and aerodynamic configuration into an operational vehicle. These must be defined even during conceptual and preliminary phases for layout and weight analysis. Subsystems include wing, tail, fuselage, flight control systems, power transmission, fuel systems, structure, power unit, which is also called as propulsion unit, landing gear, autopilot. The definitions of these subsystems influence the layout, CG, performance and cost trade-offs. This preliminary design phase, once the design is in preliminary design phase, then it will come to subsystem functional analysis. From there, it will go to design of subsystems. Once the design of subsystems is completed, then it is checked whether the requirements are met. Requirements of the design are met. If it is meeting the requirements, then we'll go for designing the components, else we'll go back to design of subsystems. If it is no, then we'll go back to this subsystems. If yes, we'll come to design components. And after designing the components, if the requirements are meeting, then we'll further proceed to design the parts and the other elements. We'll be designing the parts and the other elements of our aircraft, else we'll go back to designing components. Once the part design is done, then mathematical model and prototype test and evaluation is done. Mathematical model is nothing but CFD analysis, which includes fluent analysis, thermal analysis, structural analysis, and along with that we have wind tunnel test, prototype testing and evaluation. Once these tests are done, there will be a committee which will review this design. If they approve, it will go for release of documentations for system, production and construction, else it will go back to design of subsystems. Right. So stage wise it will take approvals and then it will come to the stage. Every stage will be approved and it will be forwarded to the next stage. Once the prototype testing, mathematical model testing is over, then it goes for final production. This phase develops a fully functional unmanned air vehicle which will have a blueprint ready for manufacturing and certification. It involves comprehensive design of every component and subsystems. The objectives and scope of detailed design phase: it uses outputs from conceptual and preliminary phases to finalize component dimensions and specifications. This design is highly iterative with multiple feedback loops, and this phase consumes the majority of design time, approximately between 10 months out of 1 year project. The major activities during detailed design phase includes sizing and definition of wing, horizontal tail, vertical tail, fuselage, landing gear, engine and subsystems. How the wing will be, what will be the shape, what will be the geometry of wing, that is being decided here. Then horizontal and vertical tails, how the elevator will be, what kind of rudder system we'll have, even that is defined here. Then fuselage, what kind of fuselage is required to accommodate the requirements. Then type of landing gear to ensure that it has a smooth landing. Then engine and subsystems, based upon the thrust or power requirement, what kind of engine is being chosen. Then once these activities are done in sizing, then the weight estimation is further carried. Then cost benefit and manufacturability analysis is done. Stability, controllability and performance modeling is being done. Design feedback loops. The detailed design phase includes 4 main feedback loops to validate and iterate the design. First one, performance evaluation. Here, the calculation of aerodynamic characteristics, especially zero lift drag coefficient, is being evaluated, and it may lead to redesign of wing or propulsion components if it is not matching the requirements. Second one is stability analysis. It determines the CG based on component weights, and failure to meet stability criteria may require changes in wing, horizontal tail, vertical tail. because these are wing is the main source of the lift. Horizontal tail is for longitudinal stability. Vertical tail is for directional stability, and this one is also for lateral stability. The wing is for lateral stability, right? So these parameters, like wing is for lateral stability, horizontal tail is for longitudinal stability, vertical tail is for directional stability. If there is the requirements, the results are not matching with the requirements, then it may require changes in wing, horizontal tail and vertical tail. This is control analysis. Design of control surfaces such as elevator, rudder, ailerons. If UAV is uncontrollable, we have to redesign the control surface sizing and engine placement. In flight simulation, it simulates full flight profile with autopilot integration. Deviations or instability in simulation can lead to autopilot redesign, changes in weight distribution or control dynamics. In extreme cases, poor results in stability or controllability may necessitate returning to the conceptual phase for major reconfiguration. In case if the stability and controllability are not matching with the requirements, there is constantly, if it is not matching the requirements, then in the conceptual phase we'll go for major reconfiguration. It will go back to conceptual phase from the beginning, then again conceptual phase has to be reframed. After that it will go to preliminary design phase, then detailed design phase, and then it will go for construction and fabrication. Design reviews and evaluation. Design reviews are formal checkpoints conducted at the conclusion of each major phase. They verify alignment with performance, safety and mission goals. Purpose of design reviews. First one, to validate the design against initial specifications, document system capabilities, identify and fix design issues at the early stage. This is the review team. CDR, conceptual design review, which evaluates the design at the end of the conceptual phase, and the purpose is to verify the feasibility and configuration layout. There is another team which is PDR, that is preliminary design review team, which verifies the design at the end of the preliminary design phase, where it verifies the size which is confirmed and subsystem integrations. So we have evaluation and test review team, that is ETR, which is in the midway in the detailed design, which will fix the component level issues and verify the systems. FDR, final design review team, which verifies at the end of the detailed design to ensure the readiness for the production. These are the design teams which will verify the design of the unmanned air vehicle or aircraft at the end of each phase: conceptual design phase, preliminary design phase, evaluation and test review, and then FDR, final design review. ETR is the evaluation and test review team, which will be working at a critical mid-stage activity to deal with the detailed design, and the role of this team ETR is to ensure design problems are identified and fixed at component level. UAV capabilities are verified and documented for certification. Conclusion: UAV design proceeds in three main phases, that is conceptual, preliminary and detailed design. Each phase refines the system with increasing accuracy and complexity. Subsystems must be defined early to enable reliable layout and performance analysis. The detailed design phase is iterative and includes performance, stability, and control evaluations. Iterative. Formal design reviews ensure that the system meets its mission objectives at every stage. These are the references used for the lecture. Reference 1, Design of Unmanned Aerial Systems. Reference 2, Aircraft Design, a Conceptual Approach by AIAA. And third book is Introduction to Flight by J.D. Anderson. Thank you. We'll meet in the next lecture.